Hi guys, this is the asynchronous lecture of week 11 of CSCIC 311 programming languages. It will focus on LL1 parsers. After this lecture, you will be able to learn the LL1 parsing algorithm. And in particular, you will learn two approaches to the LL1 parsing, including recursive descent parsers and table-driven top-down parsing. The materials of this lecture are based on section 2.3.1 and 2.3.3 in the textbook. First, let's go over an overview of LL parsing that you learned from the previous lecture. Recall that the LL class of linear time parsing algorithms has the following four properties. It scans input left to right. It discovers leftmost derivation. It constructs a parse tree in the top-down fashion. And it uses predictive algorithms. In this lecture, we will learn about LL1, which is a subclass of LL, in which it uses just one token of lookahead. To illustrate LL1 parsing, let us consider the grammar for a simple calculator language. Recall our convention for writing grammars that all non-terminal symbols are written italic, like this one. In this grammar, program is the start symbol, which describes a program generated by this language. The first rule or production means that a program is a statement list ended with double dollar sign. Note that this end marker token is produced by the scanner at the end of the input. The second rule means that a statement list is either a statement followed by a statement list or just an empty string. Recall that the epsilon denotes an empty string. The third rule means that a statement is one of three forms. Okay? The first form is an assignment, which assigns an expression to a named variable. The second form is to read a value into a named variable, which is an identifier. And the third form is to write an expression to the output. An expression consists of a term followed by a term term. A term term is either an empty string or a sequence of add of, then a term, then a term term. The second part of the grammar defines the term non-terminal and the add of non-terminal of the language. A term consists of a factor followed by a term, a factor term. A factor term is either an empty string or a sequence of mount up, then a factor term. A factor can be one of the three forms. The first form is an expression enclosed in parentheses. So an open parenthesis and a closed parenthesis. The second form is just an identifier, and the third form is just a number. So those are the three forms for factor. Add of is either plus or minus sign, and mount of is either an asterisk, which denotes multiplication, or a forward slash, which denotes division. An example of a program generated by our calculator grammar is this program, which we call the sum and average program. This program reads in values into variable A and then variable B, then assigns the value of A plus B to the variable sum. Then it writes both the value of sum and the value of sum divided by 2 to the output. So how do we parse a string with the calculator grammar? We saw the basic idea in the previous lecture, which is about top-down parsing. In other words, we can parse a string with this grammar by building the parse tree incrementally. We start at the top of the tree and predict needed rules based on the current leftmost non-terminal in the tree and the current input token. The process of LL parsing can be formalized in one of two approaches. The first one, the recursive descent approach, is to build a recursive descent parser whose subroutines correspond one-to-one to the non-terminals of the grammar. Recursive descent parsers are typically constructed by hand. However, they can be generated automatically by the NT-LR parser generator from an input grammar. But handwritten recursive descent parsers are most often used when the language to be parsed is relatively simple or when a parser generator tool is not available. The second approach is table-driven. This approach is to build an LL parse table, which is then read by a driver program. Table-driven parsers are almost always constructed automatically by a parser generator. These two approaches are reminiscent of the nested case statements and table-driven approaches to building a scanner that we saw in a previous lecture. Now let's look at a recursive descent parser for the calculator grammar. Its pseudocode has a subroutine for every non-terminal in the grammar. This first part contains the subroutine for the non-terminal program, which is the start symbol of the calculator grammar. The parser also has a mechanism input token to inspect the next token available from the scanner and a subroutine called match to consume and update this token. The subroutine match verifies that the next token is the one that was expected as specified by an argument. And if so, then it will consume the input token. If match or any other subroutine sees an unexpected token, then a syntax error has occurred. For now, we assume that the parse error subroutine simply prints a message and terminates the parsing. The parser begins by calling the subroutine program. If the initial token is either an identifier, or read or write or the end marker, which is the double dollar sign, then it calls the subroutine STMT list and then attempts to match the end marker. Otherwise, it produces a syntax error. The second part of the recursive descent parser for the calculator grammar consists of routines for the non-terminals STM list and STMT, which stand for statement list and statement respectively. When the STMT list routine is called, it checks if the current input is an identifier or read or write, and if so, it calls the STMT subroutine followed by the call to the STMT list itself. And this call matches the first productions for the non-terminal STMT list. If the current token is the end marker, then the STMT list subroutine simply returns because that case corresponds to the epsilon production for STMT list non-terminal. In the STMT subroutine, it checks if the current token falls into one of the three cases: ID, read, or write. Each of these cases corresponds to a production whose left hand is STMT. The case of ID predicts that the first production for STMT should be used because the right hand side of that production starts with the token ID. Similarly, the case for read predicts the second production for STMT, which is read ID, and the case for write predicts the third production of STMT. In each case, it just makes a sequence of subroutine calls corresponding to the right-hand side of the production predicted by the case, where each terminal corresponds to a marked invocation, and each non-terminal corresponds to a call to the subroutine with the same non-terminal name. For example, in the case of write, it calls match of write, then calls ESPR subroutine, because this case predicts the production for STMT whose right hand side is write ESPR. This is the third part of the recursive descent parser for the calculator grammar. It consists of the subroutines corresponding to the non-terminal EXPR, term tar, and term. In the subroutine for EXPR, there's only one production with EXPR in the left-hand side. And when we expand the right-hand side of this production in the leftmost derivation manner, we have term expands to factor and then factor 12, and factor expands to one of these three strings, starting with the open parenthesis or ID or number. So we only predict this production of XPER if the current input token is one of these tokens, that is either the open parenthesis ID or number, so as shown here. The predict set for term is same as or similar to that for the XPER. So here the input tokens that we use to predict the expansion for the term here are just like the open parenthesis ID or number. Because when we expand the right hand side of this production for term, it also leads to the expansion for factor. In the subroutine for term 12, there are two productions for term 12. The first one will lead to strings starting with either the plus or minus. Because its right hand side starts with add off, and add off is either plus or minus. So we only predict this the first production of term 12 if the current token is either plus or minus. The second production for term 12 is the epsilon production. So we only predict it if the current token is the one that can come after term 12 when we expand the start symbol, which is a program. And it can be showed that those tokens are one of these tokens. So the open parenthesis or ID or read or write or the end marker. Part 4 of the recursive descent parser for the calculator grammar consists of the subroutines for factor 12 and factor. In the subroutine for factor 12, the way we figure out which tokens predicts which production for factor 12 is similar to that for term 12. And in the subroutine for factor, the way we figure out which tokens predicts which production for factor is similar to that for the non-terminal STMT that we had seen in the second part of the recursive descent parser for the calculator grammar. The last part of the recursive descent parser for the calculator grammar consists of the subroutine for add off and the subroutine for mount off. Both of these are straightforward from the productions for add off and mount off here. Note that without additional code, the given pseudocode of the recursive descent parser for the calculator grammar merely verifies that the input program is syntactically correct, which means when the parse error subroutine is never executed. To be used to the rest of the compiler, the parser must save the parse tree. To save the parse tree itself, we can allocate and link together records to represent the children of a node immediately before executing the non-terminal subroutines and the match invocation. We shall need to pass each non-terminal subroutine an argument that points to the record that is expanded, that is, whose children are to be discovered. And the the subroutine match will also need to save information about certain token in the leaves of the tree. And so we will not go into details of how to save the parse tree itself, but that is like the basic idea we need to do in order to save the parse tree. For the general technique, the trickiest part of writing a recursive descent parser is to figuring out which tokens should label the arms of the case statements. Note that each arm represents one production, that is, one possible expression of the non-terminal corresponding to the subroutine. And the tokens that label a given arm are those that predict the production. A token X may predict a production for either of the two reasons below. One is that the right-hand side of the production, when recursively expanded, may yield a string beginning with the token X. The other reason is that the right-hand side of the production may yield nothing, that means the empty string, and X may begin the yield of what comes next. These two reasons has been illustrated in the pseudocode of the recursive descent parser for the calculator grammar. But we will come back to this concept of prediction later. Now we switch to the second approach to LL1 parsing, which is table-driven. The idea of table-driven LL1 parsing is to maintain a parse stack as follows. First, we initialize the stack with the start symbol of the input grammar. Then we enter a loop in which it pops the top symbol called T of the stack and performs the actions based on whether T is a non-terminal or a terminal. If the top symbol T is a terminal, we predict a production whose left hand is a T and the right hand side is a sequence of terminals and or non-terminals. Then we push the symbols on the right hand side of the predicted production into the stack, but in reverse order. In particular, if the sequence on the right hand side of the predicted production is W1, W2 up to WK, then we push WK first, then we push WK minus 1, and then we push W1 last. If the top of the stack is a terminal, then we check if T is the end marker, such as the double dollar sign in the calculator language. And if so, then we stop. Otherwise, we match a T with the current token. And if T doesn't match the current token, then we produce a syntax error. The driver for a table-driven LL1 parser implements this algorithm. Here is an example of a parsed stack, which is for the sum and average program in the calculator grammar. Initially, we push a program into stack because program is the start symbol of the calculator grammar. So the top of stack is now program, which is a non-terminal. Then we predict the production program to stmt list end marker. So we push the right hand side of this production into the stack in the reverse order. So we push after popping a grammar of the stack. So now the stack has TMT list at the top. Then we produce the production as a TMT list to STMT list. So we pop STMT list off the stack, and we push the right hand side of this production into stack in reverse order. So now the top of stack is STMT, and we predict the production STMT to read ID. Then STMT is pop of the stack, and the sequence of read ID are pushed into the stack in reverse order. The top of stack is now the token read, which is a terminal but not the end marker. So after popping read of the stack, we match it with the current input token, and the match is successful. So the read token is consumed and removed from the input stream. We can continue this function until the top of stack is the end marker, or if an error occurs. You can see the entire parse stack of this example in figure 2.21 in our textbook. To predict a production, the table-driven LL1 parser needs to look up the LL1 parse table for the given grammar. The LL1 parse table is a two-dimensional table that tells which production to predict based on the top of stack non-terminal symbol and the current input token. For example, here is the LL1 parse table for the calculator grammar. The table entries indicate the production to predict where the productions are numbered from 1 to 19. Here I cannot show all of the productions. Number 1 is the first production for the first production in the calculator grammar. Number 2 is the first production for STMT list, and number 3 is the epsilon production for the STMT list, and so on. So according to this LL1 parse table, if the top of the stack non-terminal is programmed, and the current input token is either ID or read or write or the end marker, then the production to predict is the production number 1. So number 1 here, which is this production. That is the first production of the calculator grammar. A dash indicates an error. For example, if the top of the stack is the STMT symbol and the current input token is a number, then it will announce a syntax error. To write a recursive descent parser or construct an LL1 parse table, we need to compute the predict set for each production in the given grammar. The predict set of a production A to alpha is denoted as predict of A to alpha, where A is a non-terminal and alpha is a string of non-terminals and terminals. This predict set is the set of all tokens that label the arms of the case statement corresponding to the production A to alpha in the subroutine A in the recursive descent parser. For example, the predict set of the production stempty list to stempty list consists of 3 tokens: ID, read, and write, because these tokens produce this production in the subroutines for stempty list. So that is here. Similarly, the predict set of the epsilon production for stempty list consists of only the n marker, because the n marker produces the epsilon production for stempty list in the recursive descent parser. Recall that a token X may predict a production A to alpha or belong to the predict of A to alpha for either of 2 reasons. The first reason is that the right-hand side of the production, which is the non-terminal A, when recursively expanded, may yield a string beginning with X. The second reason is that the non-terminal A may yield the empty string or epsilon, and X may begin the yield of what comes after A. This notion of prediction is formalized by defining 2 sets, first and follow. For any string alpha of terminals and non-terminals, the set first of alpha is the set of all tokens that could be the start of a string obtained by recursively expanding alpha. More precisely, in the set notation, first of alpha is defined as the set of all token C such that alpha derives after 0 or more replacements to a string starting with C. Recall from the previous lecture that this symbol, so a double arrow and then an asterisk, means derives after 0 or more replacements. So this is the notation from the derivation that we learned from last lecture. Also here we will use a new meta symbol, which is similar to the other one, except that we replace the asterisk with the plus. So this symbol means that derives after 1 or more replacements. So for any non-terminal a follow of A is the set of all tokens that could come after A in a string obtained by recursively expanding the start symbol of the input grammar. More precisely, follow of A is a set of all tokens C such that C could come after A when deriving the start symbol after 1 or more replacements. So here S denotes the start symbol of the input grammar. Now let's see an example of how we calculate the first set in the calculator grammar. Recall that this is the formula for the first set of alpha, where alpha is any string of terminals and non-terminals, including the empty string. So if a C is a token, which means it's a terminal, then the first of C consists of the token C only, because you cannot expand a terminal. In particular, the first of the N marker token consists of the N marker token. To calculate the first of program, we notice that a program can only be expanded to empty list followed by the N marker. Then the first of program must contain the first of empty list. And because empty list yields epsilon, the first of the program must also contain the first of the N marker. So because of this production and because of this fact, so here when we say empty list yields epsilon, it means empty list derives 0 or more replacements to epsilon. So we already know the first of the N marker. So now we need to calculate the first of empty list. When calculating the first of empty list, we notice that there are two productions to expand empty list. But one is the epsilon production, which leads to nothing. The remaining production has the right hand side being empty, followed by empty list. So the first of empty list must be equal to the first of the sequence empty, then empty list. The first of this sequence starting with empty must contain the first of empty, and because empty does not yield epsilon, so the first of the sequence starting with empty does not contain anything else. So therefore the first of empty, then empty list, it is equal to the first of empty. So therefore the first of empty list, it is equal to the first of empty. And when calculating the first of empty, we notice that there are only 3 productions to expand empty. And in the first production, it leads to a string starting with the token ID. In the second production, it leads to a string starting with the token read. And in the last production, it leads to a string starting with token write. So the set of first empty consists of 3 tokens: ID, read, and write. So we put this result back to the formula for the first program. So we have the first of program consists of ID, read, write, and the N marker. Now we will see examples of calculating the follow sets in our calculator grammar. This is the formula for the follow set of non-terminal A. So to calculate the follow of A, we need to try all possible ways to expand the start symbol and see what token can come after symbol A in those expansions. When we expand the program symbol of the calculator grammar, we will never see program again. So therefore, the follow a program equals the empty set. So this is the notation for the empty set. And when we expand the program symbol, the only token that can come after the non-terminal ST empty list is the end marker. So follow of ST empty list consists of just the end marker. To calculate the follow of ST empty, we notice that when expanding a program, ST empty appears for the first time in the string ST empty list, and then the end marker. This string can expand to ST empty and then the end marker because ST empty list can yield the epsilon or the empty string because it has the epsilon production here. So the tokens that can appear after ST empty in this expansion are those in the first of ST empty list, and in addition to the end marker, because here the end markers appears after ST empty when we expand the program, and everything that can come at the first of the expansion for ST empty list will also come after ST empty in this expansion. So a follow of ST empty is the union of the first of ST empty list and the set consisting of just the end marker. And since the first of ST empty list has been calculated to be the set that consists of 3 tokens, ID, read, and write, the followed of ST empty equals the set of ID, read, write, and the end marker. After calculating first and follow sets, we can now calculate the predict set using the following simple formula. The predict set of the production A2 alpha is equal to the first of alpha if alpha does not yield the empty string. Otherwise, the predict set of the production A2 alpha equals the union of the first of alpha and the follow of the non-terminal A. For example, in our calculator grammar, the predict set of the production ST empty list to ST empty list is equal to the first of ST empty followed by ST empty list because the string ST empty followed by ST empty list does not yield the epsilon string. And we have calculated the first of this string ST empty followed by ST empty list to be the set that consists of 3 tokens, ID, read, and write. So the predict set of this production is equal to the set of ID, read, and write. The predict set of the epsilon production for ST empty list equals the union of the first of epsilon and the follow of ST empty list because here, so epsilon here is alpha in this position. So because here epsilon yields epsilon, and we already calculated the follow of ST empty list to be the set of towards the end marker. And so the union of these two sets, the first one is just the empty set. So the second one is this set, so it is equal to the set of the end marker. Note that the calculator grammar we use as example in this lecture is LL1, but not all grammars are LL1. The given grammar is not LL1 if in the process of calculating predict sets, we find that some tokens belong to the predict set of more than one production with the same left hand side. Because then we would not be able to choose which productions to employ when the left hand side is at the top of the parse stack.